Yeah, welcome everyone, and thank you for joining us today. In this session, we'll be diving into the fundamentals and operations of steam turbines and how they play a crucial role in ensuring efficient and reliable performance in industrial and power generation settings. We'll begin by introducing the team who bring a wealth of knowledge and hands-on experience in energy operations and maintenance management. Over the course of this webinar, we'll walk you through the core principles, operational dynamics, and maintenance consideration of steam turbines. So you can expect to gain a thorough understanding of different types of steam turbines, their working principles, and practical insights into their operation, troubleshooting, and optimization. So this session will also highlight best practices that can enhance the performance, safety, and longevity of your turbine systems. So let's get started by introducing the team and get ready to apply these insights to drive operational excellence in your own organization. Yeah, for today's webinar, we are glad to introduce our team, Jose Enrique Montero, and he is the founder and CEO of 𝗬𝗊 and O&M consultant, having 15 years of extensive experience in energy projects in 6 different countries. He started as an operator and continued learning to become a O&M manager. With 𝗬𝗊, he would like to offer you the opportunity to continue growing in your career with training programs. And our another key team member, 𝗙𝗂𝗧𝗂𝗍. She is O&M management consultant 𝗬𝗊, having experience of over 10 years in renewable energy and 5 years on the mining sector. And she also having extensive experience as a control room operator, shift supervisor, and operations manager. And now I introduce myself. I am 𝗚𝗙𝗧𝗂𝗍𝗺, O&M management consultant, having 18 years experience in the power sector. I worked extensively in both operations and maintenance, and also in design and detail engineering for various power plants. 11 years at 𝗦𝗁𝗡𝗺 CSP in India, handling diverse roles such as executing election commissioning, then working as a control room operator, operations manager, overseeing all plant maintenance, annual outages, and regulatory compliance. All right. Now we are going to briefly present the company. We recently branded the company as 𝗬𝗊 Energy O&M Services. We are an energy operations and maintenance services company that specializes in providing comprehensive solutions to optimize the performance and efficiency of energy projects. Energy O&M services personnel has played a pivotal role in several high-profile projects across the globe, where our expertise in thermal storage, solar field, steam generation systems, steam turbines, etc., is bringing a wealth of knowledge to help our clients. So, our team has contributed to projects in diverse locations such as USA, Chile, Spain, India, Denmark, South Africa, and the UAE, applying best practices and innovative solutions to optimize energy projects. So in each of these regions, we have improved our skills in the commissioning, operation and maintenance of complex systems and ensuring peak performance and reliability. Though these international collaborations, we have gained such a valuable experience that allows us to deliver tailored services that meet the unique need of each client. So move the next slide to see the services what we offer. So we have 3 main services we offer. Operational consulting services. So we can perform operational assessments, reviews or audits, and also procedure instruction and checklist development. EPC to commissioning and commissioning to O&M transition support, operational management system and software optimization, automation and plant performance optimization, remote monitoring support, on-site operations support, and hands-on and theoretical training. And this is our another service what we offer, maintenance consulting services. So we'll give maintenance strategy, implementation and management, outage planning and supervision, CMMS development and optimization, management of change, engineering evaluation and design, solar field optimization, warranty claim management, and supplier spare parts warehouse management. And this is our another service, O&M software and hardware distributor. So CMMS software, operational and performance software, digital checklist and logbook, plant equipment, and robotic and drone inspection. So this is the agenda for the today's session, where we'll be exploring the fundamentals of operations of steam turbines. And our goal is to build a strong foundational understanding of how steam turbines function and their critical role in industrial and power generation environments. So at the end, we'll have a dedicated section for Q&A to answer some questions from the audience. And feel free to type the questions in the chat in the teams. So we have 10 agendas. So by the end of this session, you have the tools and knowledge to understand, operate, and optimize steam turbines effectively within your organization. Well, we begin by discussing the key objectives for today's session. Understand the working principle and types of steam turbines. Identify key components and their functions. Interpret performance parameters and efficiency metrics. Recognize common operational challenges and maintenance practices, and also implement the best practices. So this is the section 2, and it is speaks about the introduction to the steam turbines. So what is a steam turbine? Well, a steam turbine is a mechanical device that converts thermal energy from pressurized steam into rotary motion. And this rotary motion is then used to generate electricity or drive mechanical equipment in industrial applications. As the steam turbines are a core technology in thermal power plants, particularly in fossil fuel, nuclear, and even solar thermal energy systems, where heat is used to generate high pressure steam. So when we see the historical background of the steam turbines, the idea of using steam for motion dates back to the 𝗘𝗚𝗺 of 1st century AD. In 1884, Sir Charles Parsons invented the first practical steam turbine, and it revolutionizing electricity generation. And his innovation replaced less efficient reciprocating engines and laid the foundation for modern thermal systems. Coming to the steam turbine role in the power generation. So steam turbines plays a central role in power generation, especially in thermal-based electricity production. So they are the link between heat energy and electrical power. A steam turbine is a mechanical device so that extracts energy from high pressure, high temperature steam and converts into rotational energy. This rotating motion is used to spin an electrical generator, which then produces electricity. In combined cycle power plants, steam turbines operate with gas turbines to enhance the efficiency. So because of their higher power output, capable of generating hundreds to thousands of megawatts, and it is also suitable for baseload generation and providing constant power to the grid. And steam turbines, it provides high efficiency in combined systems. Steam turbines versatility of heat sources, and it provides the grid stability as a synchronous machine. It contributes to inertia, frequency regulation, and voltage stability. So what is the role in the industrial process? The steam turbines. So beyond the power generation, steam turbines are essential in industries like energy, petrochemical and refineries, pulp and paper, sugar and fertilizer plants. They're used to mechanically drive compressors, pumps, and fans, especially where steam is already part of the process. Global relevance. Well, steam turbines generate a significant share of the world's electricity. So they offer high efficiency, longer operational life, and flexibility in handling varying steam conditions. Even as the renewables grow, steam turbines remain vital for baseload power and hybrid energy systems. Coming to the section 3 speaks about basic thermodynamic principles. Basic thermodynamic principles. To understand how steam turbines operate, it is essential to grasp some fundamental thermodynamic principles. So these concepts explain how energy is transferred and transformed through steam, especially during its expansion in the turbine. Here we can see the Rankine cycle. So the Rankine cycle serves as the primary model for analyzing steam turbine performance. Pressurization of water in a pump, heating in a boiler to produce high pressure steam, expansion in a steam turbine to produce work, and also condensation in a condenser to return water to the pump. So here in the image we can see the pump, the water is pressurized in the pump and it is going to the boiler and it is heated, and the heat water or the steam is going to the turbine. Once the work is done, it is going to the condenser and the condenser condenses the steam and again it returns back to the pump. Coming to the enthalpy, entropy, pressure, volume relationship. Enthalpy H, it measures total energy internal plus flow work in steam. It is crucial for determining turbine output. Whereas entropy S, it indicates the level of disorder, helps assess energy losses and cycle efficiency. And pressure volume PV relationship. As the steam expands in a turbine, pressure drops and volume increases. So this expansion drives the turbine rotor. So these thermodynamic properties are visualized on TS temperature entropy and HS enthalpy entropy diagrams, which are essential tools in turbine analysis. Here we can see the HS enthalpy entropy diagram or Mollier diagram. So this Mollier diagram is named after a Richard Mollier, a German professor. So he introduced the enthalpy entropy HS diagram, which became foundational in thermodynamics. And his work was primarily motivated by the need to simply complex steam calculations for use in steam turbines, compressor, and refrigeration systems. Here we can see the blue line that separates the wet steam region and the saturated superheated steam region. And also the green line tells us about the ideal expansion path, isentropic. Think of this as a perfect path for steam flowing through a turbine. It means no energy is wasted due to friction or heat loss. Here we can see the red line, that is the expansion path. Because of internal friction and losses in the turbine, the steam does not follow the ideal green line. Instead, it follows the red line, which drops more steeply. So this means energy is wasted and the final steam quality or moisture energy is a bit worse than the idle steam. Expansion of the steam process. During expansion in the turbine, high pressure, high temperature steam enters the turbine nozzles. It expands through turbine blades, causing pressure and temperature to drop and velocity increases like in a jet. So this is the first major conversion, pressure energy to the kinetic energy. And the kinetic energy from this expansion is transferred to the turbine shaft as a rotational energy. So this is the second conversion, kinetic energy of steam to mechanical energy or shaft rotation. So this is the core energy conversion process in a steam turbine and determines its efficiency and performance. Coming to section 4, in this section we learn about the different types of steam turbines. So understanding the various types of steam turbines is essential for selecting the right design for specific applications, maximizing efficiency and ensuring operational reliability. So this segment categorizes based on steam flow direction, axial flow and radial flow, principle of operation, impulse and reaction turbines, and end-use applications, condensing turbines, back pressure turbines, extraction and reheating turbines. Axial flow turbines. So an axial flow turbine is a type of turbine where the working fluid, typically steam or gas, flows parallel to the axis of the rotation of the turbine rotor. So in this turbine, fluid enters and exits the turbine in the same general direction along the axis of the shaft. So it is most common design in power plants, and the benefits are high efficiency, better for larger capacity turbines. Examples are large utility scale turbines. Radial flow turbines. A radial flow turbine is a type of turbine where the working fluid flows perpendicular to the axis of the shaft. That is, the fluid moves inward or outward in a radial direction rather than the parallel, as in axial turbines. So these turbines are especially used in small scale power generation, turbochargers and process equipment. In a radial turbine, the fluid enters or exits the impeller radially, either from the center outward centrifugal or from the periphery inward centripetal. So the benefits, compact design and better for small loads or specific mechanical constraints. Impulse turbines. An impulse turbine converts the pressure energy of steam into kinetic energy through nozzles and then uses the high speed steam jet to push impulse the turbine blades, making the rotor to spin. So impulse turbine operates on Newton's second law. A change in momentum of steam produces a force or impulse on the blades. So steam expands completely in stationary nozzles before hitting the rotor blades, and high velocity jet impinges on blades, transferring kinetic energy, and the pressure drop occurs only in the nozzles. Example, D-level turbine, Pelton turbine. Reaction turbine. So a reaction turbine is a type of turbine that generates torque through both the pressure and kinetic energy of a fluid. Here, the steam expands gradually in both stationary and moving blades. Pressure drop occurs across both stationary and moving blades, and rotor blade acts like nozzles and providing reaction force. Examples are Parsons turbine and Francis turbine. It is used in both larger capacities and small retrofit projects. Here we can see the key differences of impulses versus reaction turbines. Whereas the impulse, it is high speed. In the reaction, it is lower speed. In the impulse, it is low torque. In the reaction, it is high torque. In the impulse, it is suitable for smaller stages, whereas in the reaction, it is better suitable for larger stages and higher efficiency. Condensing turbines. So a condensing turbine is a type of steam turbine used primarily in power generation, where the steam expands to below atmospheric pressure in the last stage and is then condensed into a water in a condenser. So exhaust steam into a condenser to maximize the energy extraction. It is commonly in utility power generation. The benefits, it is having the highest efficiency. Coming to the back pressure turbines. So a back pressure turbine is a type of turbine used primarily for combined heat and power CHP or industrial process, where steam is expanded only partially and the exhaust steam is intentionally kept at high pressure for use in industrial process. So exhaust steam used for process heating in industries, and no condenser pressure is controlled at exhaust. So the benefits, combined heat and power applications, and the examples, paper mills, sugar factories, textile refineries, and petrochemicals. Coming to the extraction turbines, an extraction turbine is a turbine designed to extract steam at one or more intermediate stages. During its expansion, this extracted steam at a controlled intermediate pressure and temperature is used for process heating, preheating water, feed water or industrial uses, while the remaining steam continues to expand in the turbine to generate more electricity. So this allows simultaneous production of power and steam in an efficient and flexible manner, making extraction turbines ideal for combined heat and power applications, industrial complexes, and power plants with feed water heaters. Reheat turbines. Reheat turbines improves efficiency by reheating the steam between turbine stages, reducing moisture content and increasing the work output. So in the reheat turbine, steam is partially expanded, reheated, then expanded further. So it reduces moisture content in the low pressure stages, and the benefits, it increases the efficiency and also the blade life. Coming to the section 5, in this section we learn about the major components of the steam turbines. So steam turbines are complex machines made of precision engineering components. So each component plays a vital role in the efficient and reliable conversion of steam energy to mechanical power. So in this session, we'll break down the major components and their functions within a turbine system. So casing and rotor, blades and diaphragms, bearings and seals, steam chest and nozzles, hydraulic or electronic governing systems. Yeah, here we can see the steam turbine picture indicating all the major components. So by the way, at the end, we'll provide the complete infographic of steam turbine with parts and its description. So in this image, we can able to see all the parts and components. Here, the yoke and seat assembly, pilot valve, servo cylinder, holding down bolts, front and rear bearings, front pedestal, rear pedestal, front and rear steam glands, front and rear bearings, and outer casing, bladed rotor, and also the wheel chamber, and also the GBC guide blade carriers. So the casing, the steam turbine casing is the outer shell or enclosure that houses the turbine internals, rotor, blades, and diaphragms, and also contains and directs the flow of high pressure steam. And casing maintains structural integrity under high pressure and temperature, and also it ensures safe operation by withstanding mechanical and thermal stresses. So the main functions of the casing, so it for the pressure containment, steam flow control, and it gives mechanical support, and it gives safety barrier, and features like inlet and exhaust ports for control steam entry or exit, and also flanges and bolting for assembly and tight sealing, insulation cladding, it minimizes the heat loss and protects the personnel. So different types of casings like split casing, horizontal and welded casing or barrel type casings are there. Rotor. Rotor is a rotating component with multiple blades attached to the shaft, extracting energy from high pressure steam and converting it into mechanical energy. So the rotor is a long, high-strength shaft that runs throughout the center of the turbine. So it carries the moving blades, rotating blades, and is supported by bearings at both ends. As steam passes over the blades, it causes the rotors to spin at high speeds, usually 3000 RPM or more, depending upon the frequency of the systems. And function of the rotor, it converts steam energy into rotational motions, it transfers torque to the generator and also supports turbine blades. And the material, it is solid forged rotor, entire rotor made from a single forged piece of steel. So rotor is usually made from high alloy steels, example chrome, molybdenum, nickel alloys. So in order to resist the centrifugal forces, thermal stresses, corrosion, and erosion from the wet steam. So the rotor is literally the heart of the steam turbine. So everything revolves around it, and any damage or imbalance can lead to major outages. So it is recommended to do the high speed balancing during the major outages. Coming to the blades, so blades on the rotor is moving blades and stator or fixed blades. So the shape and angle designed to extract maximum energy from the steam. So subjected to high thermal and mechanical stresses, so the blades of the turbine has airfoil shape. When the high energy fluid passes over its airfoil shape, it will create a pressure difference. So this will subsequently create the lift force. So here we can see the moving blades and rotating blades, stationary or fixed blades, and the flow pattern of the steam. Here the steam is entering into the turbine and it passes through the stationary nozzles, then to the rotating blades, and it passes to the different stages of the blades, and it goes to the exhaust of the turbine. Diaphragms. So diaphragms are the stationary assemblies holding fixed blades and nozzles, and it also guides steam flow and support rotor positioning between the stages. And it is essential for stage-wise energy extraction. So because of their robot design, it has been cast or forged and it is split, it has in split assembles. So it ensures durability under high pressure, high temperature conditions and facilitates assembly and maintenance. Bearings. Coming to the bearings, this is the white metal bearings, also called Babbitt bearings, or a critical component in steam and gas turbines, where they provide low friction, high load support to the rotating shaft rotor. So these bearings are lined with a thin layer of white metal alloy, which includes tin, lead, antimony, and copper. So giving them excellent properties for lubrication and durability under high speed and high load conditions. So basically it supports the rotor and maintain the alignment. And in the steam turbines, they do not use the rolling elements like roller balls or rollers, but instead rely on a film of lubricating oil to separate the shaft from the bearing surface. So here we can see the journal bearings. So it will support the rotor and gives the radial support to the rotor. And it is lubricated to reduce friction and heat. And here we can see the lube oil port here. So the oil enters through the port or grooves and forms a wedge under the rotation. So between the shaft and the bearing, the oil wedge or the film formation has to occur. So maintaining a clean oil will give proper wedge formation. If any dust or foreign particles and contamination, that leads to block the ports, and sometimes it will scratch the white metals and it will causes the bearing damages. So here we can see the image. It is a tilt pad journal bearing, and different types of bearings are there, like lobe bearing or plain sleeve or oval type bearings are there. Coming to the thrust bearings. So thrust bearings plays a critical role in turbines by supporting axial loads. So that is forces that act along the shaft axis. So thrust bearings prevents the rotor from shifting axially, ensuring proper alignment and safe operation of the turbine. Absorb axial thrust loads and maintain the rotor alignment, protect against mechanical contact. Here we can see the tilting pad active and non-active thrust bearings. So usually during the turbine startup, the non-active pads temperature will increase. And once the the turbine is in loading, and the temperature in the active pads will increase. So here we can see the active and non-active pads supported by the sleeve, and here we can see the RTD. So we can able to read the temperature of the active and non-active pad thrust bearings. Blank seals. So Coming to the gland seals, certainly gland seals play a critical role in steam turbines, especially at the points where the rotating shaft exits or enter the turbine casing. So the gland seal ensures steam does not leak out of the casing and the air does not leak into the turbine or the air ingress along the rotor shaft. So especially it is important in the low pressure section where the vacuum may be present. So types, labyrinth seals, carbon ring seals or mechanical seals, and it is essential for efficiency and safety. Here we can see the steam inlet in this image. So in this image, we can see the typical sealing system image. So here at high pressure end, sealed steam is injected inward toward the turbine to block outward steam leakage. At low pressure end, sealed steam is injected outward to block air from the entering the casing under vacuum conditions. So, and the leak of steam is drawn from the middle of the gland and sent to the gland steam condenser. So, when gland steam leak will occur if the clearances of the seals are on the higher side. So by maintaining the proper gland seal, steam pressure and temperature are essential in steam turbines. So if the clearances are on the higher side, there is a possibility that rotor may be rubbed or intact with the seals and the gland sealing will pass and the steam leak will be on the higher side and that will lose our efficiency. Steam chest. Coming to the steam chest, it is the entry chamber where the steam is admitted into the turbine and it regulates and directs steam to the nozzles or control valves. So here we can see the valve seats which is uneven and it will open as per the lift. So during the major outages, it is recommended to test the valves by DP test or ultrasonic to find out any cracks and also change the gland rings of the spindle here to avoid the steam leakages. So in continuous operations of turbines, so here the ESV is also present. So ESV partial stroke test that needs to be performed to avoid choke or jam of the pistons. So in some turbines, sometimes if the more than the 100% load, if the load is not achieved, so we have to check the fifth cone whether it is lifting or not. Based on that, we have to adjust the lift on the side. So it is essential and we have to look after it. Nozzles. Coming to the nozzles, it converts pressure energy of steam into velocity. It directs high velocity steam jets onto turbine blades. It is key in impulse turbine stages. So wheel chamber or a wheel. So it is recommended to always check the wheel chamber pressure during the startup and how much pressure is taking to start or spin the rotor or spin the turbine in rotation and the pressure draws if the pressure draws higher means there is a possible damage or aging of the system. So always have be vigilant. So how much of the pressure is taking in the wheel chamber to start or spin the turbine into rotation. Coming to the governing system, hydraulic or electronic governing system. So it controls steam flow based on load demand or operating conditions. So it maintains desired turbine speed and load sharing. Coming to the hydraulic governing system, so it uses oil pressure and servo mechanisms to adjust control valves. And also traditionally it used in larger and older units like the flyball. So the steam will enter here based on the differences of the speed. The flyball will operate and the hydraulic governor will give signals to the control valves and it will open and close. Based on that, the RPM will increase or decrease. Electronic governing system. So in the electronic governing system, it uses the sensors, controllers, and actuators. So it offers faster more precise control with diagnostics and automation capabilities. Coming to the section 6, in this section, we can learn about the governing and control systems. So coming to the governing and control systems, the governing and control system is the brain of the steam turbine, ensuring safe, stable, and efficient operation. It regulates speed, manages load, and provides protection during faults with interfaces, plant-wide automation systems. So this section gives an overview of the core governing functions and the evolution into modern digital controls. Here we can see the speed sensor signal that feeds to the Woodward governor from the turbine. So, and the signal from the Woodward governor, it feeds to the hydraulic converter, and the 4 to 20 milliamps goes to there. And here it is converted to 1.5 to 4.5 secondary oil pressure or control oil pressure. So based on that, the CV position and the steam flow will vary. Coming to the governing systems, there are speed control, load control, and emergency and trip systems and modern digital turbine controls. In the speed control, the objective is we have to maintain constant turbine speed regardless of load changes. Whereas in the load control, objective is adjust the steam flow to match power output with respect to the load demand. Coming to the emergency shutdown and trip systems, so it protects turbine and plant in case of unsafe conditions. And in modern digital turbine controls, DCS or PLC integration, so traditional or mechanical hydraulic systems are being replaced or integrated with a DCS or PLC based solution for faster response. The speed control. So our objective is in order to maintain the constant turbine speed regardless of load changes. So how it works? So turbine speed sensors feed the data to the governor, and as it compares with the reference speed, and based on the difference, the subsequent open and close of the control valve will happen. So the governor adjusts the steam inlet valves to maintain the set RPM. Here we can see the control loop, how it is operating, and the applications. It is critical in grid connected systems and synchronous speed control, and also important in standalone mechanical drive applications. And also here we can see the graph, so that provides the recent grid failure in Spain. Load control. So what is the load control and what is the objective? So our objective is in order to adjust the steam flow to match power output with load demand. Mechanism sensed via generator, load or mechanical output. Governor opens or closes control valves based on the load requirement. So load sharing, it is essential in multi-unit operation for balanced distribution. Coming to the emergency shutdown and trip systems. So the purpose is to protect the turbine and plant in case of unsafe conditions. So it triggers includes overspeed, high vibration, lubrication failure, high exhaust temperature or pressure anomalies. So the trip mechanisms instantly shuts off the steam by closing emergency stop valves, and interlocks ensure that the safety before restart. And also never bypass the trip systems because it will lead to catastrophic accidents. So whenever an outage is completed, make sure all the trip systems are active, or check the trip systems to ensure it is responding well, or it is tripping well based on the trip conditions. Coming to the modern digital turbine controls, DCS or PLC integration, it's a digital evolution. So traditional mechanical or hydraulics governing systems replaced or integrated with DCS or PLC based solutions. It features like real-time monitoring, alarms and diagnostics, and it enhances precision and faster response times. And it also gives remote operation, trending and historical data logging. And it also integration with seamless interface with plant-wide control systems and also customizable logic for complex operation strategies. Coming to the section 7, in this section we'll learn about the performance parameters and monitoring. So the efficient turbine operation hinges on tracking the right performance metrics from isentropic efficiency to vibration and steam consumption. So these indicators helps us spot issues early and also improves the output and reduce energy losses. So in this section, we break down the key parameters. So every operator should monitor and how the data trends turn into actionable insights. So monitoring the key turbine performance metrics is essential for maximizing efficiency, ensuring reliability, and driving data informed decisions. So in this efficiency metrics, heat rate, power output and steam consumption, vibration, steam and metal temperatures, and pressure monitoring, data trends and interpretation. So why we have to care about the efficiency? So the efficiency metrics tells us how well the turbine is performing. So they help plant operators and engineers know if the turbine is running optimally or wasting the energy. Coming to the isentropic efficiency or thermodynamic efficiency, imagine if the turbine were perfect, there is no friction, no heat losses, it would extract the maximum possible energy from the steam. So this is called the isentropic or ideal process. But whereas in the real life, the turbine always loses some energy due to friction and heat losses. So we compare the actual performance to this ideal performance. Whereas in the mechanical efficiency, so even after the steam turns the turbine blades, some power is lost through friction in bearings and in mechanical drag and other rotating components. So mechanical efficiency measures how much of the steam energy that reaches the shaft is actually converted into useful rotating power. So what is heat rate, what is power output, and what is the steam consumption? So what is the heat rate? Think of it as how much energy do we need to make 1 unit of electricity. If the lower the heat rate means higher the efficiency and less fuel needed and it lowers the cost. And higher the heat rate means higher the lower the efficiency and more fuel wasted. For example, if a turbine has a heat rate of 9,000 kilojoules per kilowatt hour, it means it needs 9,000 kilojoules of heat energy to make 1 kilowatt hour of electricity. So why does it matter? A lower heat rate saves fuel and money. A higher heat rate, that means the turbine is not running efficiently, maybe due to maintenance issues, old design, or poor steam conditions. So our goal is always try to lower the heat rate to improve the efficiency. Coming to the power output, so how much electricity is the turbine generating right now? It is measured in megawatts, and real-time monitoring helps operators to know if the turbine is performing as expected. So why does it matter? So turbine needs to match what the grid power network needs to, and too low means grid might not have enough power, and if it is too high, that means that can damage the system or cause the imbalance. So always our goal is to keep power output within safe and planned levels. Coming to the steam consumption, so what is it? So how much steam we are using to generate a 1 megawatt electricity? If you need more steam to make the same electricity, it means the system is less efficient. If you need less steam, your turbine is running better and more efficiently. So why does it matter? So steam is costly. So it comes from burning fuel and boiling the water, and a lot of the process will occur. So less steam per megawatt means better performance and lower operating costs. For example, a good turbine might use 5 tons of steam per megawatt. If it starts using 6 tons per megawatt, something is wrong. Maybe it is fouling because of wear or poor steam quality. And in some turbines, it is more or less 3.9 to 4.5 tons per megawatt it will take. Based on the turbines, it may vary. So our goal is reduce the steam consumption per unit of power to boost the efficiency and save the fuel. So vibration, temperature, and pressure monitoring. So vibration monitoring. So all the machines will shake a little when they run. So that's normal. But if they shake too much, it means something's went wrong, like a wheel wobbling in a car. So why do we check the vibrations? In order to catch the problems early. So vibration causes because of the misalignment. So misalignment due to parts are not lined up correctly or the alignment is not done properly or not maintaining the proper clearances and all. So the imbalance of rotating parts, blades or shafts, and they are not balanced well. Sometimes the rotor fins are not fixed well. Sometimes the loop parts that will create the vibrations. Bearing wear. Bearings are worn out and causing extra vibrations. So why is this so important? If we catch these problems early, we can fix them before the turbine breaks down and causes an unplanned shutdown, which is very expensive. Temperature monitoring. So we check the temperature of important parts of the steam turbines, like metal temperatures of blades. If the metal can weaken, if it gets too hot. Coming to the bearings, it may seize because of the high temperature. If it's too hot means it will lose the friction and it will lead to damage of the bearings. And coming to the seals, it may fail because of overheating and it also causes leakages. So why is this important? If the metal temperature goes too high, blades can crack or deform or bearing seize, and also the seals can fail and starts leaking and the efficiency will reduce. So that and also the steam temperature in and outlet and casing temperatures always to be monitored because the differential expansion in the turbine affects because of the change in the steam temperatures. So the casing temperatures gives a further loading allowance and restrictions based on the temperatures in the steam turbines or casing in the turbines. And coming to the pressure monitoring. So we measure the pressure of steam. So the live steam pressure is entering into the turbine and how much powerful the steam is entering, and also the monitoring the exhaust pressure that is coming out of the turbine and how much pressure remains after doing the work. So why is this important? So stable steam pressure means steady and efficient turbine operation. If it is too high, it risks of damage to pipes or equipment. If it is too low, means the turbine won't produce enough power. So in this data trends and interpretation, so harnessing the power of historical and real-time data and trends allows predictive maintenance via condition-based analytics, root cause analysis RCA for performance drops, data driven optimization for better output and longer equipment life. Coming to the section 8. In this section, we'll learn about the operational and maintenance of steam turbines. So in this section, in the operation and maintenance section, we can see the startup and shutdown procedures, routine checks, common failures, predictive maintenance, and condition monitoring. Coming to the startup and shutdown procedures, so startup, uh, in the startup, pre-checks like lube oil system, whether it is working, whether it is running, whether oil pressure is there or not, and also the gland sealing, proper steam pressure, gland sealing temperature, and also that turning gear is in operation or not. So that is the pre-check, and also the warm-up. So in the warm-up, gradual steam admission, we always have to take care to avoid any thermal stresses in the turbine. So that causes damages in the rotor or some bend in the rotor. It will happen because of the differential temperatures. Coming to the rolling and synchronization, so it will accelerate to rated speed, synchronized with grid or mechanical load. So coming to the shutdown, load reduction, control load drop to minimize the stress, steam cutoff, close the control valves, and coasting and cooling down. It allows the rotor to coast down with cooling systems are active. Turning gear. So post shutdown to avoid the turning gear has been engaged in order to avoid the short bowing. So skipping the startup and shutdown checklist and also bypassing the alarms leads to catastrophic failures in the turbines. And always follow the startup curves during cold and hot startups, and also ensure every permissive or satisfied. If override any of the permissives, that will cause differential temperature and also leads to rotor deformation uh, and causes major damages in the turbine. And also, while in the turbine operation, check the time in idle speed of the turbine and also the critical speed, whether it is crossing the critical band within the speculated time, and also check the time during the coasting down of the turbine. And also, always be attentive while the turbine passes the critical band. And while the synchronization, it is always recommended in order to do the synchronization in auto. So, and turning gear engage and disengage, we always have to be more vigilant and more careful. If we stop early the turning gear without cooling down, so that will cause the rotor to be deformed, or it will bow and it will cause the damage to the rotor. So always follow the ONM preferences and how much time we have to wait to totally stop the turbine and the turning gear. So the routine checks, in the routine checks, always we have to must be carried out without exception, as they provide critical insight into the health and operational status of the turbines. So daily and shift-wise checks include lube oil pressure, lube oil level, and lube oil temperature. So bearing temperatures, vibrations, gland sealing pressures, and steam leaks, drain system functioning, and also rotor axial and radial play, if we can able to measure. And coming to the drain system, and a lot of the plants, they never have a look of the drain systems, because some plants it has been directed to the condenser, it is in a closed loop, so there is no chance to check. So this leads some of the drains has been clogged or being choked, so that leads the condensate water is not passed through the drain systems, and it is accumulated on the turbine casings, and it may cause damages to the turbine and also the blades. So always ensure the drain system is working properly. Blade erosion. So it is a common failures in the steam turbines. It is caused by wet steam, impurities, or droplet impact. So blade erosion in steam turbines is a critical maintenance and reliability concern. So it refers to the loss of deterioration of blade material due to mechanical, thermal, or chemical processes. So most commonly from the impact of moisture droplets, solid particles, or aggressive chemical compounds in steam flow. It causes of blade erosion in steam turbines. So wet steam erosion occurs in low pressure stages where steam becomes saturated or wet. So water droplets in the wet steam impact the blades at high velocities, causing pitting, scalloping, or grooving, especially near the trailing edge of the turbine. So we can able to check these kind of blades or the blade erosions whenever the turbine has been stopped, or when we have taken the minor outages, we can able to insert the boroscope. So there is a certain instrument with a eyepiece and a camera with light with the insertion tube. We can able to insert in the turbine, so in a dedicated inspection ports or access holes to examine the internal components like compressor blades or turbine blades, stators and guide vanes. And one more common failure of bearing wear in turbines. It is a critical issue that can compromise performance, and reduce operational efficiency and also lead to costly downtime or catastrophic failure. If it is not detected early, effects of it will be breakdown, and the effects of bearing wear or increased shaft vibration and instability, and rotor rubbing against the stator or seals, and loss of misalignment, affecting blade tip clearance and efficiency, and also overheating and potential bearing seizure, and also potential rotor bowing or fatigue leading to failure. So during bearing inspection, it is recommended always check the bearings, whether it is a minor outage or it is a major outage. Always check the bearings, and also we recommended also put the spare bearings in a good condition, and it is in a good manner. The store, whenever there is a probable damage, we can able to replace it immediately. And we always recommended that the bearings have to be checked with the DP test or ultrasonic test to check any flaws or cracks in the bearings. So, and one more common issue is due to because of lube oil contamination. As I earlier explained that due to the contamination of the lube oil, foreign particles or some dust particles are passed through these lube oil ports, and while in the high speed, it will remove the white metal on the bearings, and also it also damages the bearings, and also it makes the scratches on the rotor also. And one more common failures, that is gland leakage. Gland leakage occurs because of loss of sealing, steam, or erosion of gland segments that leads to steam leakage and reduce efficiency, and also it will raise the concerns of safety. And following are the causes for gland steam leak: worn or damaged seals, improper gland steam pressure, shaft misalignment, and wrong clearances. And already I earlier said that so the steam gland clearances, if the alignment is not done properly, so the rotor will rub with the steam glands or the oil glands, so that will create the leakage in the steam glands or in the oil glands also. So as the oil glands or the steam glands, when the clearances are on the higher side, Sometimes the steam will slowly go along the axis of the turbine and it enters to the oil seals and it will mix up with the lube oil and it will contaminate the oil. And sometimes if you did not maintain the proper lube oil pressure, so that will pressurize that oil and it will comes and gusts out of the oil seal if the oil seal clearances are higher. So it will pass through that rotor and it will enters into the gland sealing steam. So always maintain recommended pressure and temperature both in the lube oil and also in the gland sealing, and also maintain proper clearances while doing the outages of steam turbine. And also during every shift, please check the gland drains if any traces of oil is present or not. So that is also one of the important point we all have to check. That will shows the early signs of leakages. Sometimes it is not seen. And yes, yeah, gland leakage will also cause major problems like it will it will causes fire in a lot of the turbines. So always be attentive, and also whenever there is a chance, please rectify the gland seals and always maintain proper clearance for the glands, both in oil and steam glands. Coming to the predictive maintenance and condition monitoring. So predictive techniques like vibration analysis, we have to done the vibration analysis, and we also have to check the whether the all the vibration sensors are reading well, and we have to do the inspection or calibration of the sensors. So that is so important. Sometimes this wrong signals or wrong data will lead to turbine trips and all. So the vibration analysis has to take place, and also the vibration sensor has to be inspected and also done the calibration in intervals, and also the thermography analysis, and also the oil analysis, ultrasound testing, and it detects issues before the failure occurs. So coming to the condition monitoring system, CMS, it is integrated with DCS or PLC for real-time monitoring. So the trend analysis and the alerts help we can able to plan timely interventions. So we can able to reduce the downtime of the turbines. So the benefits, it minimizes the unplanned outages, and also it will extend the life and improves reliability, because a lot of the plants they won't go further maintenance, and if the plant is running, so why we have to take the major outages? They are skipping the major outages and the minor outages. Sometimes they're not performing the condition monitoring. So if we did not done this, so we cannot able to find out the issues, and all of the sudden the equipment or the turbine will stop working and leads to major outages, and and that outtime is more. So coming to the section 9, in this section, so we can learn about the case study or real plant insights. So introduction, the real life experiences from operating steam turbines provides valuable lessons in troubleshooting and performance optimization. So this session shares practical insights into a turbine trip incident and a case of performance improvement through operational challenges. So example of a turbine trip and a troubleshooting scenario. And the event is sudden turbine trip during load operation. So the indicators are overspeed alarm, vibration spike, and main ESV activation like that. So the root cause analysis says Initial findings, the control valve sticking due to sludge in the hydraulic activator, and the secondary issues, delayed signal from the speed sensor caused by loose terminal. And the corrective actions, cleaned and flushed the hydraulic control line, and also replaced and calibrated speed sensor. Conduct a full trip test to validate response times. So always in this scenario, we can clearly understand in the root cause investigation, the control valve is sticking due to a sludge in the hydraulic actuators. Yes, because sometimes if we did not perform the oil analysis, low oil analysis, so if the NAS value is higher and the water parameters are in the higher side, and we did not check the oil properties, so that will cause the control valve sticking. And also sometimes the contaminations are in the higher side, and sometimes people won't change the filters. So regular timely changing the filters, mobile filters or control filters, is essential in the turbines, because it will avoid this contaminations, or some foreign particles will not allow into the governor control system. So it is always essential to always test the lube oil in a timely interval. And also I already speak tell about the vibration spikes. Sometimes the vibration sensor not calibrated well. Sometimes there is a loose connection. Sometimes operators know, yeah, why we have to check the plant is running well. So some in the over a period of time there is a loose contact. Some sensors may damage, or some sensor tips may damage. So this will cause the vibrations spikes and all. And also the ESP activation. So yes, sometimes we have to check whether the ESP is activated or not, because during the turbine trip conditions, if the ESP is not activated, there is a chances of over pressurization in the turbine chest, like that. So for that, we need a proper training of operators for quick diagnostics during a trip in the event, and also regular checks of the instrumentation and the sensors. It is essential. So performance improvement via operational changes. So the initial condition noticed higher than expected steam consumption and lower power output, and isentropic efficiency measured at 68%. It is below expected 75%. So the operation analysis identify early opening of extraction wall leading to steam loss. So gland steam pressure slightly below the optimal value. So this is the operation analysis, and actions taken. So adjusts the extraction valve control logic, and also tune gland ceiling steam pressure to design value, and also rebalance stage loading via control valve stroke, and also optimization. So that will improve the isentropic efficiency from 68% to 74%. So steam consumption almost reduced to approximately 6%. So stable power output with lower vibration and exhaust temperature. So the turbine issues and the possible causes in the following table we can see. So the issues of the high vibrations because of the rotor imbalance or misalignment, bearing wear, blade damage, or steam disturbances and shaft rub. So the rotor imbalance will occur because of misalignment, or some because due to not maintaining the differential temperatures. So that will cause the rotor to imbalance. And Sometimes the rotor fins are not fixed properly. Sometimes there is a loose in the blades, and it is not fixed properly. And is there any loose components in the rotor that cause imbalance or misalignment, or sometimes the balancing disc in the balancing discs, any balancing weights or being slip. So that will also cause the rotor to imbalance. And also the bearing wear, as I earlier said, bearing wears because of not performing the uh, bearing inspections, minor bearing inspections, and also not performing the bearing tests like DP or some ultrasonic tests. This will cause because the bearing wears will cause because of lube oil contamination. So and the rotor between the rotor and the bearing there is no lube oil film formation. So that causes more heat and friction. So that causes the bearing wear, and it will eliminate entire white metal on the bearing, and the bearings will damage and the vibrations will occur. Sometimes there is a possible of blade damages because of the blade erosion and possibilities of blade cracks and all, and also because of the steam disturbances, the high vibrations will occur, and because of the shaft rub. So while we are not maintaining the proper differential temperature in the turbine, so the rotor expansions falsely and the casing is not expanded in the time. So this will cause the rotor will get intact with the stator. So sometimes the pins may rub. So entire rotor will not rub, but the fins on the rotor will rub, and sometimes it forms a deep grooves on the wheels, or it will worn out all the rotor fins, and it will cause heavy vibration. Coming to the overheating of bearings because of inadequate lubrication, already I said if the lube oil ports are not cleaned, if it is clogged, because of that reason, the proper lubrication is not there. So it will cause the overheating of bearings and also excessive load. Sometimes the oil cooler issues, as the oil coolers, sometimes we did not have a look on the oil coolers, so that will causes the issue. Sometimes it is not working, or sometimes in the three-way control valves which have to pass that hot oil to the oil coolers in order to cool. So if it is not opening properly, so the hot oil coming out of the cooler is directly fetched to the bearings, so that will overheat the bearings and cause the bearing damages, and also leakage, and also vacuum issues. So that causes the overheating of the bearings. Reduce power output. So low steam parameters, blade fouling, wall leaks, and also low condenser vacuum. So that will reduces the power output. A lot of the turbines. So we can see there is a lot of the leaks and the low vacuum running the turbine in the low vacuum. So that is the major causes for the reduced power output. So coming to the vacuums, a lot of the time uh, people don't perform in the helium gas test, or some foam tests. So in order to find out any leakages or any gaps, so if we tied that and we can able to avoid the vacuum losses, so we can able to reduce the power output in the turbines. So turbine trip based on the over speed or high vibration because of the vibration temperature, and also lube oil loss, and also the control malfunction, sometimes because of the manual trip. So these are all the conditions for the turbine trip. So control wall issues, already I said a couple of times that hydraulic oil contamination, so that causes the hydraulic system or the governor system, it starts giving fault and it is not operating properly. It will get stuck and sometimes it may not operate. So that is a major causes for the controllable issues. I recommend always check the oil and do the analysis, and if the oil is too bad, replace the oil with a new oil. So in order to safeguard your turbine and also safeguard your governing control systems and so precise parts. The noise and unusual sounds that is happened because of the blade flutter or some loose and also the high pressure leaks or the loose parts or because of the vibration resonance. So this is all the causes that will happen. These are the issues that will happen common in the turbines. Maybe there may be more issues, but so these are the major causes and frequent issues that the people are facing in the turbines while in the operation. So a lot of the people are facing the turbine trips. So and some of the causes are there here. So and people are not noticed some of the possible causes. So that will causes the turbine trips and also it will lead to catastrophic failures. So I request always ensure do the predictive analysis and also check each and every components and whatever the things we have explained. Please done the routine and thorough check on the turbines in daily day-to-day manners or the shift-wise manners in order to avoid the turbine breakdown and also in order to avoid the catastrophic accidents or some casualties. So yes, and now I'm moving to a different slide. So this is different graph. So I'm showing. So this is the recent grid collapse. Well, on April 28th of 2025, a significant power outage affected Spain and Portugal, disrupting electricity supply across the Iberian Peninsula. So the blackout began at approximately 12:33 p.m. local time, following a sudden loss of 15 gigawatts of power energy. Here we can see. So ruling out of or preventing a grid collapse like the one recently experienced in Spain. So it involves a combination of engineering controls, real-time monitoring, operational resilience, and infrastructure upgrades, and also maintain grid inertia and frequency stability, and also strengthen auxiliary services and reserves. And we have to improve the real-time monitoring and control SCADA EMS systems. We have to reinforce interconnections and load shedding schemes. And also we have to manage the renewable penetration intelligently and also conduct regular stress testing and simulations and also to ensure the cyber and also the equipment reliability. So Q&A session. Coming to the Q&A session. So, okay. So let's see some questions in the chat and discuss about them.
Thank you, Kisho, for a great presentation. At this point, I don't see any questions in the chat or in the Q&A, and would like to encourage our guests to type in any questions that they might have, and we are here and happy to answer them. So please don't hesitate to reach out if something comes up to mind, even after the session. We appreciate your questions and your comments. I think back to you, Kisho, to wrap up. If something comes up, I will let you know.
Yeah, thank you, Lebo. Yeah, we hope you found the content valuable and applicable to your work. So we are excited to share that this is just the beginning. and we are going to be hosting more webinars in future. So covering the key topics related to operation and maintenance of energy projects. So we also want to make sure these webinars are as relevant and useful to you as possible. So if there are specific topics, if you like us to cover in the upcoming webinars, we would like to hear you, your suggestions, and also feel free to share your ideas with us via LinkedIn. And also, if you have a topic in your mind, and let us know, you can able to drop a mail in info@energyomservices.com, and also stay tuned for updates on our next sessions. And also, if you like the free webinar, and also please give us a positive review and recommendation on LinkedIn or Google Maps, and we'll appreciate, and it will help us a lot to continue creating these free webinars in the near future. And also thank you all for participating in the today's webinar on Steam Turbine. We hope the insights and the strategies shared have been valuable to you. So as we conclude, I want to take a moment to emphasize the unique services offered by 𝗂𝘂 Energy O&M Services. We are your trusted partner in O&M consulting services, and also dedicated to ensuring your operations run smoothly, efficiently, and with a focus on continuous improvement. And our deep expertise in process automation enables your organization to optimize plant process, reduce manual operations, and significantly boost the productivity. So our performance monitoring support provide you with real-time insights so you can make data-driven decisions to maximize operational performance, whether it's on-site or remote support. So our dedicated team is always ready to deliver customized solutions and that address your unique challenges. So stay efficient and stay empowered, and we'll see you at the full training course. And also thank you so much for attending, and thank you Jose, and thank you Libo, and thank you Beatrice for creating all these things and supporting, and thank you all one and all for attending this webinar. Thank you.